So now we will go to the tetrahedral complexes. Now the tetrahedral complexes. In tetrahedral complexes, the ligands approach in between the axis, in a direction in between the axis. Therefore, you see that out of the 5 d orbitals, the 3 d orbitals dxy, dxz and dyz, there the electron density is concentrated more in between the axis. The lobes are along in between the axis, so what happens is they will experience a greater repulsion than the two, that is dx square, y square and dz square orbital, because for them the electron density is along the axis. So therefore here the splitting will be as, it is not as in octahedral complexes, it will be just opposite to that. So 5 d orbitals, they will experience, they will get excited when ligands approach the metal d orbitals, then they will split into two, the one with the lower repulsion, that is Eg orbitals dx square, y square and dz square, then the one with the higher repulsion, that is dx, that is T2g orbitals. Now the difference between these two energy splitted orbital is called the tetrahedral splitting energy. Now if this is 3 by 5 of delta T, and this is 2 by 5 of delta T, and the configuration is as in octahedral complexes. They will follow the Hund's rule, then Aufbau principle following that, the electrons will be distributed. Now the delta T is quantitatively, it is only equal to 4 by 9 of delta O. Delta T is equal to 4 by 9 of delta O. Therefore, this in tetrahedral complexes, low spin complexes are very rare, because the electrons, the pairing energy of this complexes will be higher than the delta T, that is tetrahedral splitting energy. Therefore, the electrons will go to the T2g orbitals. So, if it is one electron here, second electron here, third electron will go here, because the delta T, this value is much low, delta T value, and this delta T, that is tetrahedral splitting energy, will be much less than pairing energy. So therefore electrons will jump here. So the outer d electrons will be taken for hybridization, and therefore this low spin complexes are very rare in tetrahedral complexes. Now those facts which couldn't be explained by VB theory could be explained by this crystal field theory. That is, why for certain ligands this pairing is taking place and why certain ligands pairing is not taking place. See, for ligands like ammonia, etc., the splitting is very high. The splitting will be very high between T2g and Eg orbitals. Therefore, it will be very high. Therefore, pairing energy will be less than splitting energy. So, what happens? The electron will get paired 1, 2, 3, then 4th will go here. The electrons get paired, then inner d orbitals are available for hybridization or forming bonds with the ligands. Therefore, they form low spin complexes easily, or since the splitting is larger. Now for fluoride ion and all, the splitting is very small. So pairing energy will be greater than splitting energy, and therefore pairing will not take place. The electrons will go to Eg orbitals. Understood? So this is how it is. It explains, CFT explains why certain ligands, for certain pairing is taking place and for certain ligands pairing is not taking place. Now, if there is unpaired electron in any compound, then that will be paramagnetic in nature. So magnetic behavior can be explained. Now comes the color. Now see, when if any d electron is unpaired d electron is there, then what happens is they can get excited from this E2G to EG. That is DD transition from lower energy d orbital to higher energy d orbital by absorbing energy from visible region. So from visible region they can absorb energy and show the complementary color and therefore they are colored. Now if ligands are different, then splitting will be different, color will be different. Understood? So that is for different ligands, splitting will be different and the color will be different. Depending on the splitting produced in any orbit or splitting produced by any ligand, ligands are arranged in a series. That series is called spectrochemical series. Fluoride, chloride, bromide, etc. come in the lower region, whereas ligands containing nitrogen, that is ammonia, ethylene, diamine, etc. comes in the furthest part. Then the highest split is caused by carbon monoxide. So they are arranged in the order, so that a series is called a spectrochemical series. Looking at that series, we can find out the splitting will be more or higher. Okay.